Here's a formula. Sine of x times 0.5 times 5. Give me a paper and a pencil and I couldn't draw this accurately once, let alone 20 times in a row. But Grasshopper can, instantly. And when I change that 0.5 to 1, it redraws. Change the 5 to an 8, it redraws again. That's what math means in Grasshopper. Not solving equations, describing shapes. Let's build one. Fresh canvas. First, we need x positions. From the params tab, place a series component. Set start to 0, step to 1, count to 20. 20 evenly spaced x values 0 through 19. Now the formula. Double click the canvas and type expression, place it. Double click the expression component itself, not the nickname field, to open its formula editor. In the formula field, type exactly sine of x times 0.5 times 5. Click OK. Grasshopper reads any lowercase letters you type in the formula as a variable and automatically creates a matching input for it. Connect the series output to the x input of expression. Connect the expression output to the panel and read the 20 values. These are sine outputs, numbers ranging roughly from -5 to +5 since our formula multiplies by 5 at the end. Now place a construct point component. Connect series output to x input. Leave y at its default of 0. Connect the expression output to z input. 20 points tracing a sine wave in elevation. The x positions come straight from series. The z heights come from the formula applied to those same x values. Next, we need ground points directly below each wave point. Place a second construct point, connect series to the x again, and leave z at 0 this time. This point sits at the ground plane. Place a line component, connect the ground points to A input and the wave points to B input. This is a column field. 20 columns heights following a sine wave generated by one formula and one series. Try swapping the formula in the expression component and watch what changes. Cos of x times 0.3 times 8, a cosine wave, different frequency and amplitude. Sine of x times 0.5 times cos of x times 0.3 times 5. Two waves multiply together and interference pattern. Square root of x, rapid growth at the start that flattens out towards the end. Absolute value of sine of x times 0.5 times 6, a wave that bounces off the ground instead of dipping below it. Next component you will use constantly is remap numbers. It translates value from one range into a completely different range. Let's say you have distances from an attractor point ranging from 0 to 25 and you want those distances to drive a circle radius from 0.5 to 3. Two different scales, remap numbers bridges them. Place remap numbers from the math tab. It has three inputs: V, the value to remap; S, the source domain; T, the target domain. For the source and target domains, don't rely on typing text into the input directly. Build them properly with a construct domain component. Place two construct domain components. For the source domain, place two number sliders, set it to 0 and 25. Connect them to the A and B inputs of the first construct domain. This gives you a domain of 0 to 25. For the target domain, place two more number sliders, set it to 0.5 and 3. Connect them to a second construct domain's A and B inputs. Connect your list of distance values to V input of remap numbers. Connect the first construct domain to S, connect the second construct domain to T. The output: a value that was 0 in the source becomes 0.5 in the target. The value that was 25 becomes 3. Everything in between is scaled proportionally. Use the remapped values as circles radii, small near the attractor, large far away. One component, a full attractor driven field. Advanced challenge, a 3D math terrain. Now let's turn this grid of points into a mathematical terrain. Start by using the same 5x5 point grid you created in the previous exercise. Make sure the X series output is crafted and the Y series remains as a normal list. Create the grid using construct point. Then add a deconstruct point component to extract the x and y coordinates. Next, place an expression component and enter the formula square root of x times x plus y times y. Connect the x output from the deconstruct point to the x input and the y output to the y input. This formula calculates the distance of every point from the origin. Add a remap numbers component and connect the expression output to its value input. Create a construct domain with values 0 and 20 and connect it to the source input. Then, create another construct domain with values 0 and 10 and connect it to the target input. Copy your original construct point component and reconnect the original x coordinate to x, the original y coordinates to y, and the remapped values to the z input. The points will now rise upward based on their distance from the origin. Add an interpolate curve component and connect the new 3D points to its vertices input to generate one curve for each row. Now add a flattened tree component and connect it. Finally, add a loft component. Connect the flattened tree output to loft input. This ensures loft receives all the curves correctly. You should now have a smooth conical hill generated entirely from a single mathematical formula, demonstrating how Grasshopper can transform equations into 3D geometry. The expression component. Why we use it? Grasshopper's built-in math components, addition, multiplication, sine, and so on, each do one operation. For anything more complex, wiring dozens of components together becomes unreadable. The expression component lets you write one line of math that replaces that entire cluster. What happens internally? Expressions passes your formula as text and evaluates it once per item in the incoming list, treating each named variable as one number or vector, point, etc. per list item. It is not a script, it has no loops or conditional of its own, but functions like sine, cos, square root, absolute value, and floor are all built in. What beginners misunderstand. Renaming an input on expression does not just change the label, it changes which variable name the formula is allowed to reference. If you rename an input to distance, your formula must use distance, not x. Remap numbers. Why we use it? Real design values rarely arrive in a range you need. Distances, angles, and areas all come in their own natural scale. Remap numbers is a universal translator between any two ranges, and it underlies almost every attractor-based or gradient-based Grasshopper definition. What happens internally? Remap numbers finds where v sits proportionally within domain S as a fraction from 0 to 1. Then finds a value at the same proportional position within domain T. It is a linear interpolation, not a clamp. Right now, every parameter in your definitions has been smooth and continuous, but real buildings make decisions. This panel is open, that one is closed. This column is tall, that one is short. Next time, Boolean logic, teaching Grasshopper to think in true and false, and to split your design into groups based on the real conditions. Subscribe, see you in the next one.